Is it okay?
Yes, please start your presentation. We can see your screen and you as well. Go ahead.
Okay, thank you. Thank you. Hi, everyone, and happy Mid Autumn Day. Today is a special day in China, the Mid Autumn Festival. It's a time for family reunion and appreciation of the full moon. So, I promise we'll keep this meeting as round and productive as the moon itself. Let's get started for my talk. I am Bo Qu and come from the Department of Physics, Peking University, China. It is my great honor to give a presentation here about recent progress in perovskite solar cells. My talk is structured into three parts. First, I'll begin with a brief introduction to what perovskite is and why it is so significant. Second, I'll discuss the work we've done on perovskite solar cells. And finally, I'll conclude with acknowledgments to those who supported this research. Let's move to the first part. What is perovskite? Perovskite is a class of materials with the same or similar crystal structure as calcium titanate, and its chemical formula is AbX3, where A site ion is a monovalent organic cation or metal cation, such as Ma, Fa, or cesium. B site ion is typically the divalent metal cations, such as lead, tin, etc. And X site ion is typically the halide anions. This chart shows the progress of different types of solar cells, including conventional silicon-based cells and emerging perovskite cells. From 2009 to the present, the power conversion efficiency of perovskite solar cells has demonstrated a remarkable enhancement from an initial 3.8% to over 27%. Perovskite photovoltaic materials offer several intrinsic advantages, such as the stability direct band gap, the low exciton binding energy, the high carrier mobility, high absorption coefficient, and high defect tolerance. Despite these merits, we also face significant challenges, such as the stability issues of perovskite cells and cells, the insufficient light absorption in double perovskites, the carrier transport issues in lead-free perovskites. Therefore, addressing these challenges is critical for the photovoltaic applications. Let's move forward to the second part. What we did on perovskite solar cells to overcome some of the challenges I just mentioned. First, I'd like to discuss our work on stable fabrication of high-efficiency perovskite solar cells under humid conditions. Humidity is a significant barrier to the applications of solar cells, and we have developed an effective strategy to address this issue. As we know, FAPBI3 is a widely utilized perovskite photovoltaic material with the advantage of an ideal direct band gap of 1.48 eV for the enhanced light absorption and utilization. However, this material also has its drawbacks, such as, for instance, under high humidity conditions, the photoactive black phase perovskite is prone to undesirable phase transitions, which can significantly degrade the performance of photovoltaic devices. Therefore, the critical scientific challenges is the stable fabrication of high-efficiency FePBi3 photovoltaic devices under high humidity conditions and their operational stability issues. The coordination solvent DMSO is employed during the two-step preparation for perovskite solar cells. However, the presence of DMSO leads to water absorption, which is detrimental to perovskite crystallization. Conversely, the volatilization of DMSO makes it impossible to regulate perovskite crystallization. So there is a contradiction between the two factors. To resolve the issue, we introduced the hydrophobic chlorinated organic molecule TTM7BCZ into the lead iodide film. Due to its low surface energy, this molecule tends to aggregate and the film surface, as shown by SEM cross-section. The resulting intermediate phase film exhibits a bilayer structure, where the upper layer is an in situ formed dense and hydrophobic camping layer with a thickness of 190 nanometers. On one hand, the camping layer resists the moisture penetration. On the other hand, the camping layer suppresses the volatilization of DMSO in the underlying layer, effectively regulating the crystallization rate and ordering, thereby optimizing the crystallization quality. As verified by XRD, NMR, and GWAX, the capping layer effectively suppresses the DMSO evaporation, resulting in successful retention of DMSO within DMSO PBI2 complex, which is beneficial for improving the crystalline quality of perovskite films. The camping layer serves two crucial roles. It not only resists moisture penetration but also optimizes the perovskite crystallization process. This results in the direct formation of the desired black phase, suppression of the undesirable yellow phase. Thereby, high-quality perovskite films with low impurities, large grains, and uniform orientation were realized accordingly. To get a deeper insight, we used the in situ absorption spectroscopy to monitor the film's evolution during annually, which demonstrates that the camping layer promotes a more controlled and ordered crystallization in humid air, resulting in high-quality perovskite films. The experimental data showed that in humid air, FePBi3 perovskite films with camping layer featured the ultra-low defect density, high mobility, large grains, and uniform orientation. The KPFM and UPS reveal a more uniform surface potential, and a more favorable energy level alignment at the interface. Therefore, the in situ formed camping layer creates hormone level step at perovskite top interface, significantly enhancing the whole extraction. The perovskite solar cells were fabricated as shown by the SEM cross-section. The power conversion efficiency of the solar cells exceeds 24.5% under 20 to 60% relative humidity. Even under 80% relative humidity, the power conversion efficiency remains as high as 23.4%. Therefore, high-performance photovoltaic devices fabricated across varying humidity environments demonstrate exceptional reproducibility and performance consistency, as shown by the experimental data, breaking through the bottleneck of stable fabrication or production under high humidity conditions. We also studied the long-term stability, the stability under 85 degrees Celsius, and the stability at MPP. All the experimental data showed that the solar cells with the camping layer exhibited the superior stability. Moreover, we also changed the different active areas, electrodes, perovskite types, and chlorinated organic molecules. The experimental data implied that the in situ formed camping layer strategy exhibited the broad universality. Let's discuss another work on extending the absorption of calcium silver bismuth bromide to near-infrared region, approximately 1,350 nanometers. Double perovskite is a promising photovoltaic material with the advantages of high carrier density, low effective mass, and high intrinsic stability. However, the relatively large band gap of 2 eV limits the absorption in the visible region. Therefore, the scientific challenges urgently to be addressed is enhancing the light absorption in double perovskites. To resolve the issue, the divalent ion was chosen as the dopant to alloy into cesium silver bismuth bromide single crystals. As the doping ratio increased, the color of the double perovskite single crystals and the corresponding powder turned from red to black, indicating the enhanced light absorption. The optimal molar ratio of ion atoms relative to bismuth atoms is about 1%. The absorption edge of ion-doped double perovskite was extended to 1,350 nanometers, which is the longest absorption edge for double perovskites. Both the PL and the THG measurement revealed that ion doping would not change the band gap of double perovskites. Instead, a new intermediate band was observed inside the pristine band gap, contributing to the absorption extension. We also incorporated the transition metal ruthenium trivalent ion into double perovskites and obtained blank single crystals by a hydrothermal method. As the doping concentration of ruthenium increased, the color of double perovskite single crystals also turned from red to black. The absorption edge of the doped double perovskite single crystals, located at 1200 nanometers as shown in the absorption spectra. Near-infrared photodetectors were fabricated based on the doped double perovskite single crystals. Under 918 nanometers light irradiation, the photocurrent was doubled accordingly. Besides transition metal doping on the B side, we also explored A side cation, alloying with rubidium. With doping ratio of 10%, the band gap was reduced by 0.14 eV, and both PCE and fill factor was improved simultaneously. However, excessive rubidium doping ratio, for example 15%, leads to increased film defects, which degraded the performance of solar cells. In order to improve the double perovskite photovoltaic films, we achieved cesium silver-bismuth bromide dissolution recrystallization based on the surface reconstruction using MABR post-treatment with IPA DMSO mixed solvent. Based on the surface reconstruction strategy, the perovskite films exhibited the superior crystallinity, accurate chemical composition, low defect densities, and enhanced charge transport as confirmed by the spectroscopy and SPS measurements. The optimized solar cells fabricated in air showed both high VOC of 1.2 watt and fill factor of 0.84. Moreover, the whole transport layer free and carbon electrode perovskite solar cells can also be optimized, as shown by the red spots, indicating the universality of this strategy. We were invited to write a review on perovskite photovoltaics in Chemical Society Reviews, in which we proposed breaking the bottlenecks of lead-free perovskite solar cells by modulating structural and electronic dimensionality. The last part, acknowledgements. I'd like to thank Professor Li Xinxiao Zhijian Chen of Peking University and all the PhD students. Thank you all for your attention.